This is not a pi, what this guy is trying to say, because the likelihood is actually this guy in n time. It means f of x1, okay? F of x1 given theta multiplied by f of x2 given theta until I get to f of xn given theta. Okay, it is the product of the marginals. Why is it product? Because we believe x1 up to xn, they are independent. When they are independent, you're actually going to multiply the respective probability. Now, if I want to write it in short form, if I want to write this guy in short form, I'm going to write this guy indicates a product sign. That's what it means. Now, what I'm going to do now, since I'm having this one in n time, I'm actually going to introduce that here. Okay, I'm going to introduce that here. So my likelihood, given that, which is this, I start from that to that, the whole of that. 1 over square root of 2 pi sigma square, or this guy. Please pay attention, okay? Pay attention. You don't understand, ask me question. Let me do this. Can you see now? Okay. I want everybody to see that. Okay. Now,
Hey, on
if
the
you take a
online
look at,
section,
can you see that again?
on the online section, we can't see your screen. Like we can't see it, the whiteboard.
Oh, you can't see the whiteboard.
Yeah.
Okay.
I can see the
Mm,
whiteboard, but I can't
okay.
see it to the side.
Oh, okay.
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 Oh,
I will
then it
do
might be
this now.
me. Sorry.
Yeah, that's okay. I was, some those in the Zoom, they can't really see the whiteboard. Now, I'm gonna go back to the slide now. Now, if you take a look at this guy, 1 second. If you take a look at this guy, that is what I just wrote, right? Okay. I just put the products that this is so many. If I want to do that, that is why this guy is just going to be SI, because I have x1, x2 up to xn. I have n number of observations. Okay. Then after that, this is the likelihood now. What I identify now. Okay, so this guy is a likelihood. Okay. Now, you know, this is multiplicative. Please pay attention. What I have right now is multiplicative. Seeking the maximum likelihood means I actually want to optimize this. I want to my objective here is maximization. My objective is not minimization. That's why it's called maximum likelihood. I want to figure out the best value of the mean of the parameter that will best explain the variation in my data. Now, I want to maximize this, but you know what? Because this is multiplicative, it will be difficult to maximize a multiplicative functions. Because of that, what we're going to do, we're going to introduce a logarithm. And you know why we're introducing logarithm? When you introduce the logarithm, when you take the log of a multiplicative, it's going to become additive. When it become additive, it will be very easy to optimize. That's why you see us introducing a logarithm, because we have shown this statistically, and we've proved this mathematically, that maximizing likelihood function is the same as maximizing the log likelihood function. So we now introduce a log to both sides. Okay. Now, when you introduce a log, now let me tell you something here. If I want to rewrite this, because of this guy, what I'm gonna get, okay, mathematically, when I have a square root or something, initially I'm actually gonna have the whole of this one is gonna become 2 pi sigma squared raised to power negative half. Why do I say negative half initially? 1 over square root of something is 1 over something raised to power half. When that now go up to become a numerator mathematically, it's going to be raised to power negative half. Now, because I'm doing it at n time, this is going to be n over 2. N time to be able to apply this guy here. Now, if I want to apply this guy on the exponential raised to power that, if I have exponential in n time, that will become a summation. So this guy is now going to become exp, okay, exp that, then I'm going to have minus, then there's going to be a summation. Summation I start from 1 to n, then I'm going to have the whole of this guy. Xi minus mu divided by sigma all squared. Do you see what I have now? Okay, this now the new expression that I have now is what I call the log likelihood. I mean, it's a likelihood function. Okay, it's a likelihood function. Now, what do I want to do? When I take the log of both sides now, what is going to happen? This guy is going to come back. He's going to come, of course, you know the law of mathematics, taking the log of an exponent, the exponent is going to come down, then we're going to have log of that. Okay, you're going to have log 2 pi. Okay, and when I split this one, the logarithm of the product becomes the sum. That's why you have this guy here. That's why you have this. Now, when I take the log on the exponential, the log that I'm taking is a natural log. It will eliminate that exponential, and that was why I got this guy here. Okay, now that is my log likelihood. Now I'm set to optimize. Optimization here, we're actually going to borrow idea from mathematics. We're going to differentiate with the respect to the parameter under investigation. I'm actually going to differentiate with respect to mu. When I do that, and I set the resulting expression to 0, I'm actually going to arrive at this. I'm going to arrive at sample mean, which is summation S over n. This is the origin of the formula for mean, okay, that we use in statistics today. Now, that is when I'm actually looking for the mean. If my interest is looking for the variance, I'm actually going to come back here, okay. Instead of differentiating with respect to mu, I will differentiate with respect to that. There are 2 parameters in the normal distribution. You can all hear me, right? Okay. There are 2 parameters in the normal distribution. The parameter mu, the parameter sigma squared. Now, I will differentiate with respect to sigma squared and set to 0. So for that, then I'm going to end up, I'm actually going to get this guy here. I need you to pay attention. What has happened now? We've been able to derive the maximum likelihood estimate for mean. We've also do the same for variance. But if you take a look at the variance here, we are dividing by n. That is the difference between the least square variance and the maximum likelihood variance. The maximum likelihood variance is divided by n. You can see 1 over n. But the least square variance make use of degree of freedom. The least square variance is going to be divided by n minus 1. But let me tell you, what is the difference between the two? Let me tell you this. In hypothesis testing, in confidence interval, and so on like that, we make use of the least square variance. Okay, we make use of the least square variance. Why? Because the least square variance is unbiased. But let me tell you this. The least square variance is unbiased, but it does not have, if you compare the least square variance with the maximum likelihood variance, the maximum likelihood variance will be smaller. Let's take a look at that. When you are divided by n, and when you are divided by n minus 1, when you are divided by n, okay, will be smaller. We're going to give you a smaller value than when you divide by n minus 1. It's just like you're dividing by 10 and you divide it by 9. You divided the same thing by 10, the same thing by 9, okay? Of course, when you divide the same thing by by 10 will be higher, will be lower than when you divide by 9. But what is the benefit of this guy, of the maximum likelihood variance? The benefit of this guy is consistency. We have some properties of an estimator. We have unbiasedness, we have consistency, we have asymptotic normality, and we have efficiency. Let me tell you this. Out of the 4 properties of an estimator, the maximum likelihood actually secure 3 of them. The only one that is not guaranteed is the unbiasedness property. But let me tell you this, when the sample size is large, the maximum likelihood estimator will be unbiased. The bias is going to shrink to 0 when you are working with a large sample size. So by consistency, the variance of the maximum likelihood estimator will shrink to 0 when the sample size is large. When the variance of an estimator shrink to 0 when the sample size is large, then it means your maximum likelihood estimator will converge to the true value of parameter. By efficiency, it's actually going to be it's going to have the lower variance compared to any other estimator. By that is by efficiency. By asymptotic normality, of course, in your theory of statistics, okay, when central limit theorem take a center stage, okay, when central limit theorem take a center stage means when the sample size is large, even though your data you are not choosing that from normal distribution, but your statistic will become normal. We follow normal. We did that in theory of statistics. So this is why maximum likelihood estimate of the variance is very attractive to statisticians because it satisfies most of the properties of estimator. Okay, I'm going to give you an example before I move to the other material. If I want to figure out the violent crime rate in Minnesota, and I have data set that we collect across counties in Minnesota. Okay, now the number of counties in Minnesota become the number of observation, and you collect this based on maybe some types of variables that has to do with crime. You look at the distribution of the data, and you realize that it's normal. If distribution of data is normal, what do you need to do? You want to figure out the rate, the violent crime rate. All what you just need to do is to use the sample mean. The observed sample mean will actually give you the rate that you are looking for, which is going to be the center. But that is when you correctly specify your model, when your model is true. Because if it is not normal, if it is something else you specify model, you are not going to get it right. So the method of maximum likelihood require that you specify the correct model in the first place. How do we do this in R? Okay, it's going to be easy doing this in R. This is my data set now. I got this as my data set. I want to get the maximum likelihood estimate of mean. This is the code. I can get out of mean. I can get the sigma squared. At the end of the day, I have this result for both mean and the standard deviation. Okay, so we have programmed this behind, when you are using software and you're just having results, we program formula behind every software. whether you're using R or using Python and so on like that. Okay, do you know what we just finished? When we are assuming, we are focusing on measurement, one measurement at a time, and we believe that the probability distribution of that is normal. But you know what we want to do now? We want to talk about bivariate normal. Bivariate normal appears to situation where I got more than one variable. I got two variables. They are very jointly and they follow normal distribution. Okay, so I'm gonna stop my share now. I'm gonna share 1 second. I'm gonna share the material for the day. Okay, I'm gonna share the material now. But let me tell you this. If you understand univariate normal, it will be easy to understand bivariate normal. If you understand bivariate normal, it will be easy for you to understand multivariate normal that we want to do on Friday. The multivariate normal is now applied to when you have so many variables. Now, I want to welcome you to, it's not stage changing, but every other one look like that, right? Okay, sorry about that. I'm going to complain that to the tech. Okay, so I want to welcome you to bivariate normal distribution. We got two variables that vary together, and we investigate the probability distribution if follow normal. Now, we've achieved number one, outline number one. We are now on outline number two. Okay, now let's get started to bivariate normal. We're actually going to have an extended distribution, normal distribution to accommodate two variables. Take a look at this. Equation 5. That's a bivariate normal distribution. If you take a look at what I have right now, I'm now talking about f of x, y, x and y. Maybe x is height and y is weight. And I realize the height and weight are jointly distributed. They follow normal. You can apply this across our field. Okay. I can also apply this in polities. Okay. If I want to focus of what is happening in the United States, maybe I want to focus on a particular political party. Okay, S may represent the proportion of votes received by a particular political party in 2020, and Y is the proportion of votes received by that same party in 2024. If they are related, okay, and they follow normal distribution, we can actually use that to answer any inference problem. Now I present to you, if I ask you in the exam to state the probability density function of a bivariate normal. Okay, this is what I'm actually expecting from you. Okay, that's what I'm expecting. Equation 5. Now let us take a look at each of what we have. Oh, if this is x, maybe this is weight, or this is the mean of weight. This is the variance of weight. If this is height, if y represent height, okay, this is the mean of height. This is the variance of height. Okay, then what is this guy here? Sigma S, that is the standard deviation of the other variable, the standard deviation of the other one. Then what is rho? That is a correlation between them. Rho is a correlation between them. Do you know, if I wanted to do something now, if the correlation equal to 0, if the correlation equal to 0, you know what I'm going to have? It's going to be, it's actually going to be this guy. It's going to be this guy multiplied by the one for y. Okay, this one for x, another one for y. okay, which is what we call a situation where rho equal to 0, where correlation equal to 0, then the joint, the bivariate density function become the product of the marginals. Do you know what I call marginal? The marginal is when I'm looking at the distribution for one variable at a time. This is for x at a time. If I change it to where I have x, I change it to y, then it becomes the distribution for y. Then if I multiply them, that occur when rho equal to 0. You know what? This is just trying to tell you mean of x, mean of y can be any values in real number. Mean can be negative, mean can be 0, mean can be positive. But you know what? Variance, okay? If you take a look at what I have, when I was specifying the real number, I indicated positive. Can you see that? The variance have to be positive. The standard deviation have to be positive, okay? And of course, the rho, the correlation coefficient is that. Now here, marginally, when I say marginal distribution, if I want to focus on the variable at a time, so here I'm going to say x follow normal, here y follow normal. But if I want to look at it, in a way that they actually varies together, this is going to be the density function. Now we got a lot of parameters here. When we're dealing with this guy, just one at a time, we got only two parameters, the mean and the variance. But you know what? If you take a look at equation 5, we actually have 5 parameters. We got the mean of s, the variance of s, the mean of y, the variance of y, and the correlation, making 5. Just wanted to see that. Now let's take a look at in a situation where I have the same value for mean. If mean equal to 0, if mean of s and mean of y equal to 0, and I have different variances, and the correlation is that, how is the shape going to look like? That's what you're seeing right now. Okay, that's what you're seeing right now. Now, what if in a situation where I want to talk about different means? Okay, if you take a look at what I have, across board, I'm actually assuming that the variance of the first variable is 1, the variance of the second variable is 2, and that is the correlation. And I want to look at using this, I want to look at the effect of different means. Okay, I want to consider a situation where, okay, they have the same mean, 0, 0. Oh, they have different mean. One has 1, the other one has 2, and they have the same mean, -1, -1. I wanted to see the position of that stuff, the position of something that look elliptical. You can say it's right here, it's right in the center, right in the center here, right? But here it is not in the center. Can you see the position? I just wanted to see the way that is changing when you're trying to vary when you try to vary means. Now we are trying to vary the parameters, keeping some parameter at constant. Do you know what we're investigating here? We are investigating the effect of correlations. If I have different correlation, if other parameters stay the same, if I have the same, if mu of s, mu of y is 0, and the variance is 1, sigma squared, the variance of s is 1, and the variance of y is 2, okay, I want to look at the effects of changing correlation. Oh my God, you take a look at this. When the correlation is negative, of course, it's expected. You see that? When it is negative, right? When the correlation is positive, do you see that? Do you see that straight line? Okay. And when it is 0, when there's no correlation, then we expect to have that. Okay. We're using 2D now. We're using two-dimensional plane, to actually investigate, different correlations. Okay. I'm going to keep moving. Yeah. If I want to investigate different variances, if every other parameter stay the same, just wanted to see that. Now, and I want to go into calculus. For instance, Do you know what I want to do do you know what equation says? What to achieve? What we want to achieve with equation 6? Let's go back to clinic now. Well, I want to assume if X is weight and Y is height of my patient. Let's say I happen to be a doctor and I want to figure out what is the proportion of my patient, have weight value between a value, maybe one value on the other one. And what is the proportion of my patient having their height between two different values? That's what I want to find. I want to find what is the probability of S lie between A and B and Y lie between A and B if I actually, because of the fact that the normal distribution is continuous, it's a continuous density. I'm actually going to use the idea of integration, antiderivative. That I'm actually going to have two integral. Why am I having two integral? Because I got two variables, and I'm actually going to use f of x, y. The f of x, y in equation 5. The f of x, y here in equation 5, okay? That is, I'm actually going to perform the antiderivative on that. But you know what? That is calculus, okay? That is calculus. But let me tell you this. The idea of standardization will simplify what we want to do here. We do not need to go through calculus. And that was why I was telling you on Monday, okay, the reason why normal distribution is attractive to everyone in scientific community is because of simplicity of probabilistic computation. Why? Because we're able to standardize. When we standardize, we will be able to use a statistical table and everything become easy. Okay, now I want you to pay attention. So equation 7 now, we talk about the CDF, cumulative density. Okay, what is the probability that, what is the proportion of my patient that will have a weight less or equal to a value? I want you to terminate at a value. Or what is the probability that what is the proportion of my patient we have height less or less or equal to a value? That's what I mean by equation 7. Now moving. Now, if you take a look at this, is just to show you the picture. The image. The first one is is the PDF that we call the probability density function, and the other one is the CDF. But you know what? I want us to take a look at this. Please pay attention. We're getting there, it's getting complicated. But if you pay attention and you ask questions where necessary, you actually going to be fine. Now let's take a look at this. Let's say we want to consider two variables, X and Y, two measurements. I want it to be relating that to real life. Oh, let's say S is height and Y is weight. I got two variables measured on my patient. And the Z here is a vector. It has two variables. Because of that, I'm actually going to say the two variables simultaneously follow normal distribution. But you know what? It follows normal distribution. This guy here, this very mu, is going to be a mu vector that will contain the mean of S and the mean of Y. Then this guy here, oh my God, that guy is the variance covariance. Why am I going to have a covariance matrix? Because in the diagonal, I'm going to have the variance of S, the variance of Y. In the diagonal, I'm actually going to have the covariance of X and Y. Now, and that is why it's going to be 2 by 2. Oh my God, take a look at that. In the diagonal, you have the variance of each variable. In the off diagonal, you have the covariance. How am I going to calculate covariance? Covariance, if I want to calculate covariance, I mean this guy here. Covariance is a product of correlation and the standard deviation of each of X and Y. Because you know why? Because the correlation itself, oh my God, the correlation itself is actually the covariance XY. It's actually covariance XY divided by sigma X divided by sigma S sigma Y. And that is the reason why if I want to find this one, it's going to be the product. That's going to be the product of that. And that's what you have here too. You need that to set up your covariance matrix. It's actually going to be 2 by 2. Now, when you set up your covariance matrix, okay, and I want to move right now, I quickly want to move to something else. Now, at times you may be working with a linear combination. Okay, I think I talked about that on Monday when you're dealing with univariate. We're also going to work on linear combination where you are dealing with bivariate. But you know what? Let me first of all define my constants matrix. I can have a constant matrix that look like that. I can have that. And I can have a constant matrix that has all zeros. Now, if I know that my Z is X and Y, okay, it's two measurements, and I want to have a linear combination. Please pay attention. I want to have a linear combination of two variables. Don't forget, my Z here is actually X and Y. A here, because I got two variables under Z, then the constant matrix should be 2 by 2. If you have three variables, the constant matrix will be 3 by 3. Now, this very B here is just like an intercept. It's also going to be it's going to be a vector, which is why I'm actually saying this. Take a look at that. Now, you know what happened now? This guy is going to say, I have a new variable W. A new variable W is a linear combination of X, and Y. Now, I'm now seeking to get what will be the distribution of W. Let me tell you this. When X follow normal distribution, the linear combination of X also follow normal distribution. When X and Y jointly follow normal distribution, because here, this very Z contains X and Y that follow normal distribution, then I'm also expecting W, which is a linear combination of X and Y, to also follow normal distribution. Okay, that's what I mean. And if it follows normal distribution, what is going to be the mean of W? It's going to be A mu. What is going to be the variance? It's going to be A mu plus B, sorry. Okay, what is the mean of W? It's going to be A mu plus B. What is the variance of W? It's going to be this guy. Please pay attention. Now, I quickly want to move to something else. Now, let me tell you the beauty of a normal distribution is that when the marginal is normal, the conditional is also going to be normal. Okay? Now, the conditional is going to be normal. Now, for instance, if you take a look at this, what is the conditional distribution of Y given S? Oh, I know the percentage of voters that voted for a particular party in 2020. Can I predict the percentage of voters that will vote for that same party in 2024? You need to use a conditional for that regard. Oh, I know the mean. I know I actually know the weight of my patient. Okay, and I want to figure out the height. Okay, I will use a conditional distribution for that. Now, mathematically, the conditional distribution of Y given S is going to be the ratio of the joint of the bivariate divided by the marginal. Of course, you all remember this in probability theory. The probability of A given B, okay, A condition on B is equal what? Is equal to the probability of A intersection B, okay, A intersection B, okay, divided by probability of B. Take a look at that. And if it is probability of B given A, it's still going to be probability of A intersection B, but divided by probability of A. I just wanted to take a look at equation 8. That's a conditional distribution. Okay. And you know what? If I have a conditional distribution, I need a conditional mean and conditional variance. Okay. Now, you've done this before. This is going to be the conditional mean. This is going to be the conditional variance. Okay. Now, here, if you go back to univariate, oh, okay, it's not here. If you go back, if you go to the univariate normal, we don't have conditional mean. You know what we have? We only have unconditional mean and unconditional variance. When one measurement is involved, when one variable is involved, you only have unconditional mean or conditional variance. But right now, because there are two variables involved, this guy means I want to get the conditional mean of y given s. I already know s. What would be the mean for y? And I want to know the conditional variance for y. But the conditional mean and unconditional, sorry, the conditional mean and conditional variance become unconditional mean and unconditional variance when the correlation is zero. Take a look at this. What happened here? If this guy is zero, you're only going to have a sigma square y, which is unconditional variance. If this guy, if the row here is zero, the whole of this is going to be zero. Then you're only going to have a conditional mean for y. The only condition under which conditional mean and conditional variance become unconditional mean and unconditional variance is when there is no relationship between x and y. Of course, if there's no relationship, why am I conditioning an event on another event? I'm not going to do that. So if I now, I want to derive this, given that I know my f of x, y to be a bivariate normal, and I know f of s to be univariate normal, I'm actually going to have, that's what I'm doing here. Okay? You don't need that. And I'm just trying to show you that's what we're doing there. Okay. We know all of this. Okay? And we know that I told you equation 10, what I told you the other time is when x and y are independent, if they are not related, we're not going to have that bivariate. We're only going to have the products of the univariate normal. Okay? So I think I've walked you through that. But you know what? Before I go, what is the application of this? Okay, I just wanted to take a look at this. A statistics class take two exam, X exam 1, Y exam 2. Where the score follow a bivariate normal distribution with parameter. They have to give you all the parameters to use bivariate. How many? 5. You see the mean S, the mean Y, you see the sigma Y, sigma S, and the correlation. And the question now has, suppose we select a student as random. What is the probability that students score over 75 on exam 2? When they say exam 2, I'm only going to be focusing on a univariate for Y only because they say exam 2. But take a look at B parts. The B part said, the B part still asked the same question, but said the students score over 75 on exam 2, given that the students score 80 on exam 1. I will use conditional function. My time is up. I'm actually going to start from this application in my next class. Is there any question? I don't like rushing. Okay. Wherever we stop in a class is where we're going to start in another class. That's all I got for you today. Make sure you all stay safe and have a lovely day. See you on Friday.
I have a question
Go ahead.
not related to today's material.
Okay, go ahead.
Um, I've emailed you and the TA about a makeup date for the midterm. I emailed last week and again on Monday. So I just wanted to make sure that you were getting the email.
Okay. Thank you so much. I'm actually going to reply to that email today. And you
Okay.
know what? I'm flexible when it comes to exam. So since you've stated your reason, all what I'm just going to do, I'll ask you to make a proposal about the date. Okay?
Okay, yeah, that's what's in the email.
Okay, I will do that. I will reply to that
Awesome.
today.
Thanks so much.
You're welcome.
Bye.
Yeah, bye.